This rock, called granite, can be tooled to form many things such as building stones. Granite is formed deep within the earth and is excavated in large mines such as this one. It is not a pure substance, but is made of many different minerals that keep their individual identity. It is made of minerals such as pink feldspar, mica, and quartz. It is a mixture. A mixture is matter that is made of two or more substances mixed together but not chemically combined. There are hundreds of different mixtures, including this sand on the beach, made of different kinds of sand, rocks, and shells. This soil being tilled with this machine is also a mixture. A closer look shows it is made of different particles of dirt, stones, and plant roots. These tomatoes, carrots, and mushrooms are being cut up to be part of a mixture. The mixture is this salad being created. Mixtures are classified by how well mixed they are. As you can see, this salad does not appear to be the same throughout. Heterogeneous mixtures are substances in which the components are not evenly distributed. Vinegar and oil, seen here in two separate layers, is used as a salad dressing. It is a poorly mixed, heterogeneous mixture, and that is why it needs to be shaken before pouring. This cereal is another heterogeneous mixture. It is made up of oats, seeds, coconut, and raisins. Each component, when added to the mixture, retains its individual properties and is not chemically combined. Homogeneous mixtures, like this paint, are different from heterogeneous mixtures in that they are well mixed and the same throughout. This milk is a homogeneous mixture in that it is chemically the same throughout. Other examples of homogeneous mixtures include toothpaste. Perfume is also a homogeneous mixture. Having explored the differences between homogeneous and heterogeneous mixtures, let's consider the three types of mixtures: colloids, suspensions, and solutions. Mixtures, like paint, are called colloids. A colloid is a mixture in which the particles are mixed together but not dissolved. The particles in colloids do not settle out and are continually bombarding each other. Shaving cream is a foam that is a colloid. Fog and smoke are colloids and appear quite cloudy. The liquid on the left is a gelatin, a colloid. The liquid on the right is colored water, a non-colloid. Due to the properties of the gelatin, light can pass through it and the particles seen, but the particles in the colored water on the right cannot be seen. A suspension is a heterogeneous mixture in which some of the particles settle out. The particles and the water in this paperweight form a suspension. The water in this raging river also forms a suspension. This flask of water was taken from the silty river. Let's see what happens if we let it stand for several hours. After a few hours, you can see the water is clear and the particles have settled to the bottom. If you look closely, you can see different sizes of particles. When rivers rise over their banks, as seen here, silt and particles often drop out of suspension. "70% of the earth is covered with a very well-mixed liquid, seawater. Seawater is a solution. A solution is a very well-mixed mixture in which particles are small and most often dissolved. In seawater, many different chemicals, including salt, are dissolved in water, giving seawater a homogeneous or very well-mixed appearance. Another common solution consists of the gases nitrogen, oxygen, and other gases. It is the air we breathe. Let's make up a solution that is great to drink, lemonade. A solution has something that is dissolved and something that the substance is dissolved in. We will begin squeezing some lemons to make lemon juice. The juice from the lemon is called the solute. A solute is a substance that is dissolved in another substance. Now let's add the juice to some water. Water is the solvent. A solvent is a substance in which the solute is dissolved. To sweeten the lemonade, we will add another solute, sugar. Many things dissolve in water, and it is often called the universal solvent. In our lemonade, notice that it is the same color and taste throughout the liquid. This is a property of solutions. Most soda drinks are injected with carbon dioxide, a harmless gas that you can hear when opening a soda can. The gas gives the drink its fizz. Many soda drinks have gases such as carbon dioxide that are dissolved in the liquid.
A fun way to study how matter changes is by looking at the food you eat. Do you like pizza? Think about the ingredients that are used to make pizza. There's tomato sauce, made from tomatoes, cheese, and the crust. Before it's cooked in an oven, the crust is dough. Sticky, wet, and easy to squeeze and stretch. Dough is made from flour, water, salt, and yeast. When heat is added, the dough bakes into a hard crust. It changes from one form to another after it is baked. You probably wouldn't want to eat a pizza without baking it. Here's another example of how matter changes. How would you describe an apple? You might use words such as round, red, and hard. But after these apples are picked from the tree, they are going to be made into apple juice. First, the apples are washed. After removing all the seeds and stems, large machines press the apples until the juice is squeezed out. The juice is poured into containers, and now it's ready to drink. The apple is now apple juice. How would you describe this juice? Wet, sweet, and light brown? These words are very different from those used to describe the apple. Many people have vases and plates made out of pottery. Hard, breakable, colorful pottery comes in many different shapes and sizes. How is pottery made? And what is pottery made of? You might be surprised to learn that this hard material was once a soft, wet, slimy substance called clay. It's like mud. Clay is a type of soil found naturally in certain areas. People who work with clay are called potters or sculptors. They start with blocks of wet clay. They cut it, mold it with their hands, spin it on a wheel, and form it until it's in the shape they want. Then they let it dry in the sunlight, or they bake it in a special oven. potters may decide to decorate it with colorful paint. It is baked again. Finally, it is ready to be used or displayed. Look how this matter changed. What started as clay, a wet, thick, soft matter, was baked until it turned into a much harder matter called pottery. Matter is all around us. All matter takes up space and has mass, even if that mass is extremely small.
Did you know medieval chemists were called alchemists? They believed there were 4 states of matter: earth, air, wind, and fire. They thought a mixture of these elements created every other object on Earth.
Now it's your turn to answer a question. What is matter?
Emulsions are created by the use of emulsifying agents. When a combination of vegetable oil and water are placed in a jar, the two substances quickly separate into 2 distinct layers. When a small amount of soap is added to the mixture and the mixture is shaken, an emulsion is formed. An emulsion is a colloid created by the dispersion of one liquid in another. In this example, soap is used as an emulsifying agent to combine the salad oil and water together. Soap molecules are large, and one end dissolves in the salad oil, while the other end dissolves in the water, thus bringing the two together. This is why soaps are so effective in cleaning grease, as they attach the grease molecules to them and are washed away by the water. Emulsifying agents are also used in foods, so they do not separate. Pectin is an emulsifying agent used in many jams and jellies. Eggs act as an emulsifier for the water and oil in mayonnaise. In any solution, the substance of which there is the greatest quantity is referred to as the solvent, while the substances of lesser quantity are called solutes. Solutes are dissolved in the solvent. Dissolved solute particles are either ions or molecules. Ions are atoms with either a positive or a negative charge. Ions and molecules are so small that they cannot be seen with a typical microscope and can easily pass through filter paper. Solutes and solvents can be solids, liquids, or gases. Carbonated drinks, for example, have gas solutes dissolved in a liquid solvent. Vaporization, on the other hand, is an example of a liquid dissolving into a gas. The gas in a deep-sea diver's tank is a solution of helium and oxygen gases. The addition of a solute to a liquid solvent causes the boiling point of the solvent to be raised and the freezing point to be lowered. For example, the salt water in oceans freezes at a lower temperature than does the fresh water in lakes. There are also a number of types of heterogeneous mixtures. These include suspensions, colloids, and emulsions. Examples of suspensions are readily found in nature. For instance, a sample of the water from a muddy stream would contain sand and sediment in suspension. If the material is allowed to sit, the sand and other particles will eventually settle to the bottom. Particles in suspension are thousands of times larger than molecules and ions dissolved in solutions. Suspended particles can be readily seen with the aid of a microscope, and some can be seen with the unaided eye. Suspensions can be made more stable by reducing the size of the dispersed particles through a process known as homogenization. Milk is homogenized by breaking down the suspended fat globules into smaller particles. This helps to prevent the separation of fat solids from the milk liquid. Suspension of solids in a gas can also occur. Often when we see the sun at a steep angle, we can see the dust and pollen suspended in the air. This is called the Tyndall effect, when the light is scattered by particles in the air. In our own blood, the blood cells are suspended in plasma and can be separated out with the use of a centrifuge. Likewise, many products that recommend shaking well are suspensions, where the particles within need to be evenly distributed throughout the liquid before it is used.
In a moment, we're going to mix those together, but I want to make a point. Now look it, guys, look what I've got here. I've got a bunch of different candy, don't I?
Yes.
You know their properties, don't you? I'm going to put some M&Ms in, and some almond M&Ms, and we got a couple of different kinds of candy here. And what I'm going to do is I'm going to mix these all up. Now they're mixed. Are they the same or different?
Different.
It's mixed, isn't it? It was not mixed before. How about the individual pieces? Is this still the same as it was before?
Yeah.
The individual pieces haven't changed, have they? But they're mixed together. Do you think you could get them unmixed?
Yeah.
Could you take them apart and put them back into their cups?
Yes.
Yeah.
Easy or hard?
Easy.
How, now, you know their properties, so you could use those properties to tell which went with which. Here's something, though. What if you were blindfolded? Could you do it blindfolded?
Yes.
Yeah, you can tell by the
How would you do it?
The shape.
texture, the shape.
Okay, so like you could go, this one is squishy, and then you'd know this goes in the squishy pile or something like that. But you would do size, shape, these are hard, another one is soft. You could do it blindfolded, couldn't you?
Yes.
Well, we're in fact going to mix some things together and then see if you can get them apart. We're not going to do candy, but we are going to do some other items here. What I'm going to do is I'm going to take each of these things that we've been observing, and I'm going to mix them together. Now right now they're in layers, but I'm just going to mix them all up, okay? I'm going to stir them up, I'm going to mix them, and now we're going to need to try and separate them. Most of the iron filings are back in the bottom. Some of this may be easy, some of it may be more difficult. Your job is to get them apart. Okay, I haven't mixed it all entirely. I need to do some more mixing just to make sure that it's not too easy. And one way to do it might be to just pour it back and forth. Well, you can work on that part of the task. The most important part of the task is how will you get them apart? And you'll need to use what you know about the properties of these different materials. Remember back, some of these items were in our trays when we were observing, the salt in particular. You know some things about it. You know some things about the beads. Now, your teacher may have some tools that will help you. She's not going to tell you, or he's not going to tell you what those tools are. You're going to need to ask for them. If we give you the tools, that may give away part of the answer and you won't be solving the problem yourself. I really want you to solve it yourself. So go ahead and get started. Try to get some of these things apart from each other. Start with the easiest ones. We'll talk to you again in a few minutes. Get started. It's your time. We're getting the iron filings out using a magnet. Now let me just show you what we've done here. We've got them in a little plastic bag. That keeps the magnet clean, but you can see the iron filings there that have stuck onto it. Then they're really easy to get off of there. And what you'll notice is that that uses the property of iron filings. They'll stick to a magnet and allows us to separate those. Now you guys still have a little bit more time, so keep going. Here's the next question. How are you going to separate the next items? That's going to be harder, isn't it? Yeah. Salt and sand. I guess with a pair of tweezers, but it would take forever. So keep working, you guys. It's your time. The properties of the salt tell us that we can separate it if we use a little bit of a trick. And let's go ahead and try that. I'm going to take, here's my sand and salt, and I'm going to mix some water in there. This is a very messy program, you guys. You better be nice to your teachers because they're putting up with a big pain today. Would you guys stir that just a little bit? I'm going to grab some of this filter paper. So now it's very difficult to see, isn't it? But if what we know is correct, the salt is being dissolved in the water and the sand is not. That's the idea. Now you have some little discs like this of filter paper. If you fold these in half twice, then you get almost a little triangle shape like this. Then you can take this little funnel and you take one section and see how that works? Now I'm going to put some water in here, and that'll soak into the filter paper and kind of hold it against the edges. So now the filter paper is kind of stuck into the side there, and it fits really well into this cup. So let's see if we can give this a try where we're almost overflowing. But let's just see what happens here. I'm going to pour this in. It's kind of brown and yucky. But look at the color. Wait, see that? Look at the color coming out the bottom. It's not entirely clean, but it is much cleaner than what we have here in the top. Now I overflowed my filter paper there, so some got around the outside. So we could filter this twice and see what's going to happen. Now, partly too, what someone said is we could just pour this off and let it dry. So I can fill several cups with this. But most importantly, I can actually take this now, and the sand does not go through the filter paper. Very interesting. And if it's not clean enough, if you're not satisfied, you could filter it more than once down on the bottom and see what happens. Now we can separate the sand. That's pretty easy to do. I can let that dry and I can get the sand out. We've separated the beads and the iron filings and the sand, but the salt is now still in the water. Some of you have already started to think about that. How are we going to separate the salt from the water? Interesting. I'm not going to give you the answer. I want you guys to think about it. Would you just slide those over and get those out of the way? Here's an activity that will take some additional time on your part, won't it? But if you use what you know about the properties, then you can separate them. A big idea to remember here is that the properties did not change. When we mixed those things together, salt was still salt. Iron filings were still iron filings, and the properties of the mixture took on the properties of each of the parts. Sometimes when we mix things together, they will combine and change. In this case, they retained their properties, didn't they? That's going to be fun to watch in the next programs.